This is called the Frobenius method. So we have re-derived the harmonic oscillator spectrum using analytic method this time, right? These are actually the Hermite polynomials. Hi guys, so welcome back. Hope you had a nice week. So it's lecture 9 today that I want to talk about, and as promised in the last lecture, I would the agenda for today would be to rederive these expressions for the harmonic oscillator and these eigenspectrum using differential equations. So you recall, right? Here we sort of used an algebraic method, which I might have a lot more to say later if you guys are interested in group theory. This prescription that we used in lecture 8 actually generalizes in group theory. These are called the so-called Chevalier bases of groups. But right now, maybe that's not important. Right now, I want to rederive these equations again using standard differential equations, and the fact that you will get the same eigenvalues and the same eigenspectrum would sort of reiterate that what we did here was correct. So this is like you could call it lecture 8b, for example. Okay, so let's begin. So we were studying the harmonic oscillator, right? So goal for today is I want to show that generally the eigenfunctions, the time-independent eigenfunctions that we have been studying of late, can be written in terms of these Hermite polynomials. Do you guys know what Hermite polynomials are? It's okay if you don't, but if you do and you guys want to comment, let me know. So 1/4, then this is a normalization, in terms of the so-called Hermite polynomials. And these are called Hermite polynomials, named after the mathematician Hermite. And this is the general wave function for a harmonic oscillator. Okay, let's derive this using algebra. So let's begin. So for example, the differential equation essentially I want to solve, which would be a continuation from last week, is simply this. So let me reiterate that this is actually unknown. A priori it's unknown. You have to solve both for E and for psi, right? And this is, if you recall in lecture 8, this is exactly what we had done. For example, we had solved for the first couple of psi's. Of course, it would be infinite in number, countably infinite in number in this manner. And we also had solved for the e's, right? These are the e's. So we are at the same place. We need to solve for the psi's and the e's. And these are called the eigenvalue equations, right? We a priori do not know this. Okay. Okay, so if I were to introduce a tidier notation, let's introduce a psi. This is definition. Let's introduce it in this manner: m omega by h cross x. It does nothing, right? It's just a convenient way to reabsorb this guy so that the differential equation looks neater. In terms of these variables, your d2 psi dx square becomes is equal to psi square minus k psi with, you could ask what k is. Well, k is related to the energy. Okay, it's just that this equation looks prettier, right? It looks simpler. So it just we have reintroduced two variables, that's all. Okay, good. So basically we'd solve we'd focus on this equation now. It's the same equation, of course. The way to solve this is basically, nowadays you can really put this in Mathematica, or simply you can use Maple or Mathematica, or even ask Claude. These are AIs, right, to solve this equation for you. This is Gen Z. But generally, we will not do that right now. We'll actually solve this equation using asymptotics. So that will tell me, I mean, there's a reason for, there's a good reason for doing that, actually, because it will tell me something about the physics of the problem. Okay, if you really solve it by hand using asymptotic analysis or something. So yeah, so my suggestion, use these, but use this later when you have at least solved such differential equations by hand a couple of times. Okay. Okay, so so the equation I want to solve is here, psi double prime. Again, to introduce you to a notation, this double prime means double derivative with respect to x. You will see these a lot in maths literature. Is simply psi square minus k. This is the equation I want to solve. Let's look at the asymptotics. So what are asymptotics? Well, it tells you, maybe I directly cannot solve this equation. Maybe let's look at how this equation behaves when this parameter that you have. I should actually call this xi, right? It's derivative with respect to xi. It's the same thing, of course, because your xi is linear, is basically proportional to x, but nevertheless it should actually be xi. So I should be careful. This should actually be xi. Right. So by asymptotics, I simply mean the fact that, let's look at how this equation will behave. For example, say if this is much smaller to k, or if this is much bigger to k. So the advantage is, if, I mean, the strategy is, if xi square is much bigger than k, then maybe you can ignore k for the time being, right? It will give you an approximate solution. It's important to realize, for the time being. I mean, if you ignore k, it certainly will not be the exact solution, right? Okay, so your psi, imagine you're doing that. Imagine if si square is much bigger than k, then then your psi, you can check this, behaves like a constant times a damping factor plus another constant times a blowing up factor. This symbol means approximately. Why approximately? Because as I mentioned that you are really looking at a regime, right? So you should be clear as to what you're doing. You are looking at the solution of this equation when this parameter xi is much greater than k. So what we have done is basically you are sort of looking at rather this equation instead, right? Because we have ignored this k because xi square is much bigger than k. And the claim is the solution is given by this equation. You can double check using the derivative, double derivative, and you will get that this actually is a solution. I hope it's obvious, because if you take a derivative with respect to xi, it acts on the exponential and you just pull out a xi, which gets multiplied by xi again, so it gives you the xi square. Okay, so this is, as I mentioned, this is an approximate solution, of course. This is not the full solution because we've actually ignored k, right? So imagine as an ansatz. So now comes an ansatz. We have met the word ansatz before, right? You remember, right? When going from time dependent to time independent solutions. It will be in lecture 3 or 4 before. So if you guys are here for the first time, you guys can take a look there. So let's choose an ansatz. Let's think that your psi actually behaves in this manner. Some function of xi times e to the power minus, why? You should ask why. So what is happening? First and foremost, you see in this solution, when xi is very, very large, this solution blows up, right? This is exponential xi square. So this will not be a normalizable solution. Or in other words, if this mode is not killed off by hand, by you from outside, the maths will never tell you. But if you don't kill off this mode, or in other words, if you don't set b to 0, this psi that you have, that solution you're looking for, will not be normalizable. It's crucial to realize that if you want finite, this implies b has to be 0. And this is an important point in physics. See, the maths will never set b equal to 0 for you. It's you as a physicist that have to set b equal to 0. It's an outside input because you demand this extra condition on the normalizability of the wave functions. The maths will pop out for you both these solutions, a equal to non-zero and b non-zero. So this is where you as a physicist need to do a bit more than just mathematics, right? This is physics. Okay, then what did we do? Well, you argued that you are going to kill off this mode, so you are left with some constant times this minus xi square, right? So this guy is here, and you are assuming that the ansatz for you is that the full solution, which had a k, is of this kind. By introducing a function of xi. Here, recall that it was a constant. It was not a function of xi. So in going from k equal to 0 here to k non-zero, the ansatz is you imagine that this is not a constant anymore. This is rather a function of xi. Okay, some arbitrary function that you need to solve for. You need to figure out what this h is. This is not known. You need to solve for it. That's the math that you have to do. Okay, good. Okay, good. So in terms now let's call it a solution, say A, just to name this equation. Let's putting back. So now you have a solution. Now you have an ansatz for psi, and you want to solve for h, right? So putting A back in the original equation that you had, double derivative is equal to what was the equation? Psi square minus k. This was the equation, right? With k non-zero. Now you have reinstated back k. This equation simply reduces if I put A back to d square h square, sorry, minus 2h d psi, sorry, dh d psi plus k minus 1 h is equal to 0. Okay, this is homework. That substitute this equation A, substitute equation A into the main mother equation, and you'll get, my claim is you'll get this equation for h. Okay. You could argue that a priori this equation does not look simpler, right? I mean, you still have a second order differential equation in h instead of a second order differential equation in psi, right? You will see that this is actually simpler. A priori, it's not obvious that this is a simpler equation to solve. Or in other words, a priori, it's not obvious as to why this substitution that you did here, this ansatz, is helpful. But it is. In hindsight, it turns out to be helpful. So this is a method. This is crucial now. This is maths again. This is called the Frobenius method. It instructs you to solve this differential equation using a power series. What do you mean? You assume that the solution that you're looking for, this h psi, is of this kind. Sorry. This method is called the Frobenius method, and it's one of the standard ways of solving differential equations, in this particular case, this differential equation. Okay, that you imagine that your h has a power series expansion of this kind. Okay, so what happens when you have this? Well, it's simpler. You can just let me use the dash notation just so that you are also comfortable with the dash notation. Well, what happens to this guy? This guy is simply n equal to 1, maybe. Yeah, or maybe I can just keep it to 0, right? So an n psi n minus 1, but that wouldn't make sense because you want it to start from n equal to 1, like psi equal to 0, right? So it will be n equal to 0, n equal to 1. Anyway, because I mean, the claim is that this is the same thing as n equal to 0, right? Because the 0 term n equal to 0 will kill it off. So this is the same series, right? Yeah. So I might actually use n equal to 0, it doesn't matter. Because the n equal to 0 term is 0 actually. And likewise, you can have a double derivative. So you tell me what happens. It pulls out the n minus 1, right? And you are left with... So effectively, this series starts from, xi equal to 0. Because n equal to 0 is killed by this term and n equal to 1 is killed by this term. Okay, good. Now, with these expansions, let's call them B, you plug them back in this differential equation. Because this is the differential equation you are trying to solve, right? So this immediately will give you, n plus 1, n plus 2, a n plus 1 plus 2, minus 2 n a n plus k minus 1 a n psi to the power n equal to 0. Well, something happened here. Let me explain what I did. Basically, I took the first derivative and the second derivative and placed them back here and here. So this equation will reduce to some thing order by order, right? Times xi1 something xi2 not psi, sorry. Yeah, psi. Plus. This will be the general structure, right? And so on and so forth. So I have simply written the coefficient of the nth term. The coefficient of the nth term. This is the coefficient of xi n. Okay? Which all terms would contribute to this xi n coefficient? Well, it would be the xi n from here, the xi n plus 1th expansion from here, because there is one derivative. So you see here, one derivative reduces the xi by 1. So the xi n plus 1th term from this guy and the xi n plus 2th term from this guy will contribute, right? Because again, you see the double derivative reduces the power of xi by 2. Of course, it's the double derivative, right? Okay, good. So it's clear where this series that I wrote came from. And now you see the beauty of this method, right? This term individually has to be 0 for this equation to hold. And mind you, this is for all n, right? For all n equal to 0, 1, 2, up to infinity, right? It's only then that this full series would be satisfied. So this series would reduce itself to something times xi1 plus something times xi2 plus something times xi3, So every such coefficient needs to vanish for the series to be satisfied, right? For the series to be set to 0. So this term needs to be 0 for all n. Great. Now you see that you have a handle on already something. This tells you that your aj plus 2 or an plus 2, in this case I'm using the notation n. Griffiths was using the notation j, it's the same thing. 2j 2n plus 1, sorry, minus k right. So immediately you see something. Now it's turn to understand. If you give me a0, say it's fixed from outside, then using this recursion, this is called a recursion relation. Then this recursion relation will give me first term a2, but since a2 and a2 is given, then I'll find a4, then I'll find a6, and in principle I'll find all such terms, right? Because if I know this term, I know this term. Likewise, so you need to give me a0. This is an input from outside. Likewise, if someone gives me a1 from outside, this needs to be fixed from outside. I know, similarly, I know a3, I know a5, I know a7, and da da da, right? Simply because I know, if I know, for example, a1, I know a3. If I know a3, I know a5, and so on and so forth. Or in other words, in principle, I know this full function, right? Because this function was written in this manner. Right? So this is called the Frobenius method, and this expansion, this is the solution of the Frobenius series method of solving differential equations. Okay, good. So let's solve for a couple of them. Note something. You need to be mindful of something. Again, imagine, for example, what happens in this relation that you have. In this relation, if, again, let's just see how this recursion behaves. Again, if your n is much greater than k, then this implies your an plus 2, for example, scales as 2 by n, right? 2 by n an. Do you see this? How did I get this? If 2n is much greater than k, then I can ignore this guy. So it's 2n by, again, I can also ignore 1 and 2. So it's 2n by n square, so which is 2 by n. This is sort of the asymptotic behavior. Again, these are called asymptotic behaviors. Okay. That tells you what? Well, that tells you, I mean, if you imagine your an plus 2 is equal to 2 by n an, if then your h psi, which is basically n equal to 0 to infinity, an psi n, this behaves like what? This behaves like c, some constant c, times e to the power xi square. I hope you see this. So it again exponentially diverges. For large xi, that is large x. Recall that your xi was related to x, right? So this should not be allowed, not allowed. Well, how do you stop this? You demand that for some n equal to n star, particular value, say 5, 10, 100, 200, doesn't matter, but some fixed value, a n star is equal to 0. This is you demand. Why do you demand that? Well, because if this term vanishes, this series truncates somewhere, then you don't get this exponential divergence, right? It's just a finite number of series. So this becomes a finite term, and the psi exponent does not diverge exponentially. Is this clear? This is crucial. If you demand, let me say it again. If you demand this term vanishes for some particular value of n star, for some particular value of n star, or n star plus 2, just to be consistent with Griffiths, let me call it n star plus 2. Doesn't matter, of course, right? If this vanishes, if this particular component vanishes, then this series truncates, right? Because a n star plus 4 would depend linear, is a multiplicative factor of a n star plus 2, as we see from this equation. If a or a n star plus 2 is 0, so is a n star plus 4, so is a n star plus 6, right? So if this is 0, then all these coefficients, a n star plus 2m, say m is equal to 0, 1, 2, 3, they're all 0, right? This comes from this equation. If you have a n star plus 2 here, then the a n star plus 4 is 0. If you have a n star plus 4 equal, here you have the a n star plus 6 equal to 0, and so on and so forth, right? Which means this series truncates, and that is exactly what you want, right? Aha! But when will it be 0? So if a n star plus 2 is equal to 0, this means then, well, let's look at this equation again. Well, you certainly don't demand a n to be 0, a n star to be 0, then your entire series would collapse. Which means that this term, this numerator has to be 0, right? Do you get it? Which implies k is equal to 2n star plus 1 for some n star, which is a natural number. 5, 10, 100, doesn't matter, but something, right? Do you agree? That's the only way where you would have a n non-zero, but a n plus 2 0, because this term vanishes. This term is 0. Great. And you are done. So you see what your k was. Let's go back a couple of pages and let's see what k was. You see, k was right here. So k oops, I forgot what k was. Is 2e by h cross omega. It's 2e but we have shown that this is actually equal to This immediately implies your E do you get it? And ta-da, you're done. This was the spectrum we had found, right? This was exactly the spectrum we had found here. That the energy is given by n plus half h cross omega. Great, you're done. So even using algebraic methods, you get the spectrum for your your harmonic oscillator spectrum. En, let's call it n now. Where n belongs to some natural number. So we have re-derived the harmonic oscillator spectrum using analytic method this time, right? This is in parallel to what we did in the last lecture, where we used group theory to derive the same result. Okay, so great. Actually, as a further exercise, you can show that using these values of A that you generate from these recursion relations, given a particular value of A0 and A1, you have to tell me a particular value of A0 and A1. Using these recursion relations, you can show that this, your psi n, the nth eigenfunction, is actually proportional to the Hermite polynomials. The nth Hermite polynomial, actually. Times this e to the power minus xi squared by 2 that was there from the very beginning, right? This was there from the very beginning, using our ansatz. Where was it? Yes, here. So this term was always there, and you can show using the recursion relations that I derived for you that this h psi, there was a reason I called it h, or rather there's a reason why Griffiths called it h. These are actually the Hermite polynomials. And you can look them up in Wikipedia if you're interested about their general form. I think Griffiths gives you the first few, right? The H0, for example, is simply 1. H1 is 2x. H2 is 4x squared minus 2. H3 is 8x cubed minus 12x, and so on and so forth, dot, dot, dot. Okay. There is a Rodriguez formula for this. For h and fx. That you can look up from Wikipedia, or maybe I can discuss it next time we are studying together. Okay, so we have derived the harmonic oscillator in great details. This is what I wanted to do. And if you think that these lectures are helpful, or if you have some questions, then don't forget to comment, and of course like and share my videos, and of course subscribe. It just helps me make more useful content for you. Thank you. See you next time.